Am I showing the right screen here? Can you see my cursor?
Yeah.
Yeah, okay. So basically, I'm going to demo two bits of software here. RasCal 2, which is the one we're working on, and RasCal, which is our old one. The reason for doing this is RasCal 2, it's split into two bits, which is a calculation engine and a GUI, but there's no GUI for it yet. But it works in the same way as RasCal, so it's easier to show what's going on with RasCal if you do it that way. So RasCal 1, bless it, it's from quite old now, it's from 2007. It's specifically for multi-contrast neutrons data, and it's intended to be a very easy GUI to set up multi-contrast data. So you can do that with layers, or you can find custom models, which are either layers in terms of area per molecule and things like this, or for example, if you want, you can also define a custom XY profile, so you can have different references, and then it'll just chop things up. So cons, it's not so good for solid matter, doesn't support magnetism, you need a MATLAB license, and it's not scriptable. Okay, so you can't write a script. You could, but it would be basically a hack. So that's the reason for moving on to RasCal 2. So it's split up into two bits, RasCal 2, which doesn't exist yet, and RAT, which stands for the RasCal Algorithms Toolbox, which is coming close to release now. So this is all in C++, or nearly all in C++, there's some MATLAB in there. And it has all the scattering calculations and algorithms and scripting in it. And then the intention is RasCal 2 will be a standalone GUI that calls RAT, deals with all the things that GUI deal with. So the way RasCal basically does things, this will become obvious when we go to the next thing, is you basically split everything up. You have parameters, so you can define your thicknesses, roughnesses, and so on. And separately, you define your experimental parameters and your data. Okay, and then with your parameters, you can group these into layers. So, for example, if you had a deuterated and hydrogenated layer, these would share the same thicknesses and roughnesses, but differ into SLD. So you do these for however many contrasts you have, and then just group these together into contrasts, right? Your layers, your backgrounds, your data, your bulk phase values, and so on. So that's basically how RasCal works: is make these all separately, group the parameters either into layers and then into contrast with everything else, or you can do custom models or custom XY profiles, things like this. Right, now, okay, so I said to some of you, I've had loads of computer problems over the last few days, so MATLAB keeps crashing, and so does my VPN. So I have actually recorded the two demos. So we'll do RasCal 1 first, and then we may cut this a bit short. But anyway, here's the RasCal 1 version. So to demonstrate fitting our polymer data using RasCal 1, as I said, it's a MATLAB set of codes. So first you start MATLAB and navigate to your RasCal directory. Then you just run this RasCal, and this will start RasCal for you. And here we are, welcome to RasCal. So it shows you a few windows here. So this is obviously your plotting. We'll go through this as we set up our model. Actually, let's go ahead now. So here are your parameters. If you remember, we spoke before about how you have parameters and experimental parameters and group them. So your parameters here, we'll show how we add relevant ones here. The experimental parameters, so backgrounds, scale factors, a shifting Q, which we never really use these days, bulk in and bulk out SLDs and resolutions, and then layers, which we haven't defined any layers, and in the end, contrast. So basically, it says what the contrast name, what the data file is like, the background that it's using, the scale factor it's using, the shifts it's using, and so on. And here you can set data ranges and sim ranges. And this is the controls block that lets you run everything. But let's make a start on analyzing our polymer data. I think I set up, so let's start here. So I'll show you how you set the parameters, but well, actually, let's do that. So I've made a start here and put in the relevant parameters, but let's go straight into building the model here. The model building is done from the edit menu, and you need to go to edit project, and this opens up the model builder. On the first page here, it says what type of model it is, and then the geometry. This needs to be solid liquid. And our parameters, I've predefined these. I mean, to add parameters, you just do this, click the add parameters button, and then you type in a name for them. So this could be, my parameter or something like this, but it's a bit boring to have somebody setting all these up. So I've set all these up already. So here for our parameters, we've got a bulk interface roughness. We've got parameters for our oxide, so thickness, SLD, hydration. For the oxide always takes the same roughness as the substrate roughness, pretty much always. And then our polymer parameters, polymer thick, SLD, hydration, and roughness. And the first thing we need to do is group these together into layers. So if we go add layer, and then we can edit this. So the first layer we need is oxide. And the second layer we're going to need is polymer. And then we need to tell it which parameters we're using for each one of these. And if you click on here, you will see a drop-down layer, which has all the parameters that we've just defined on the previous screen. So we just pick the correct ones for this. SLD, substrate roughness, and hydration, which is here. And this just says which bulk interface is doing the hydration. So we're hydrating with the bulk out, which is the water here. And we do the same for the polymer. So polymer thick, polymer SLD, oops, no, sorry, polymer roughness, and polymer hydration. And on our experimental parameters, I've sort of set these up again. But here, for example, if you had multiple contrasts, then you would add, maybe, for example, you've got a H2O contrast, for example. Same if you have different resolutions across everything. Similarly for scale factor, but most of these are shared because, well, we've only got one contrast. And here is our contrast. At the moment, it's just, well, this should be silicon. I haven't changed the name of it. Actually, let's do that. We will just change the name of this here. Silicon. And then when we go to our contrast, so the name has changed here to silicon. Here, you would pick which backgrounds you on scale factors and so on you want to associate with your contrast. Again, you'll see a list if you've got multiples of them. But what we want to do now is add our layers. So we want 2 layers, one for the oxide and one for the polymers. So if you look here, the layer names, oxide and polymer. So when we go to contrast, we want silicon, oxide, and polymer. And now this is just the simulation. In fact, let's check that just to see that it's reasonable. So here we have basically our polymer layer that we've set up, and here's the simulation of it. Now what we want to do is add some data to this. So if we go again to edit project and go to our contrast, and then we want an ASCII file. And well, it seems I've already done this, but polymer data.dat is our data. And I should point out at this point that RasCal on NORAT at the moment, it doesn't deal with the 4th column of resolutions yet, because that usually doesn't come up with us for ICEs. It will be in RasCal 2. It's not quite there at the moment. But basically, so this resolution is a constant resolution across all of Cube at the moment, and that's the only option you have in RasCal 1. So this should now load in our data, and there we have our data. So for all our parameters, we have ranges. Well, actually, let's do the first thing, because this is normalized data, clearly normalized data. So here we can go to scale factor and we will just change this to 1. It already looks better. This is still air, 2.0738 to the -6. And also because normalization is always sometimes a little bit off, let's give this one a range. Let's let this one go. All right, 1.1. And that's it. We have our model set up. Again, background is a bit high here, so we've associated with this background. Actually, let's make sure we fit this. So for all these parameters, you have a little tick box here, and this determines which ones you want to fit when you're doing your analysis. So clearly our background is wrong. We want to analyze our scale factor as well, no shift, because we assume the experiment's been set up properly. D2O, we will let this fit as well, because for solid liquid samples, very often you don't get complete exchange of D2O into the cells, so sometimes, depending on how the sample's been set up. So let's fit this as well and give it a range, 5 times 10 to the -6, and we don't know what our resolution is, kind of constant resolution. That's it. So now let's just pick an algorithm. If we go to tools here, select fitting algorithm, let's go for differential evolution in this case. We don't make one, we're probably not going to need too much. So let's give it 300 iterations of this. And I just look, oops. Parameter must between bounds for oxide thick. Okay, so what have we done here? Oxide thick. Okay. We haven't set up these ranges properly. So let's give up this one 10 and let's make it go to maybe 30. Our oxide SLD, we don't actually want to fit this because this is constant. Yeah, we're probably not going to get 50% hydration. Oxide's usually about 20%. Polymer looks okay. SLD, yeah, we give it a nice big range because we don't know what this is. Began with a polymer hydration. Now we should be able to run out of it. And off goes our differential evolution. So it seems to have got there pretty quickly. You see our chi-squared coming down here. It probably is struggling out the resolution with here because if this is Ansted data, it may not be constant. There we are. Just let poor little RasCal go as far as it can. So this just showed the flaw of the constant resolution, basically, because it's overestimating resolution here, underestimating resolution over there. But like I said, this is normally built for RasCal type, MATLAB type data. So in this one, you don't have this very fourth column variable resolution, but it will be in the RAT toolbox. And that's basically it. There are various tools you can have. So, for example, you can select a Bayesian analysis if you want, which seems to be taking a long time to open. There we go. We won't run Bayes because it can take a little bit of time on. That's the hell of it. Let's just see what it looks like. Yeah, so this is going to take about 20 seconds on RasCal 1. You'll see in a bit that it's much, much faster on RasCal 2. Then it does a little bit of thinking about things. So yeah, clearly we want to set some priors. I mean, okay, our oxide thickness is hitting a limit. What's it done here? Yeah, so this gives you its uncertainties on all your parameters. You can see because the oxide thick is hitting a limit. That's clear from the shadings around here. Here's your posterior distributions. And the oxide hydration isn't really being fitted in any meaningful way. We'd probably do it setting a prior on this. There's diagnostics. So yeah, we didn't run this Bayesian analysis for long enough. You can see what you really wanted is to look like this along the whole range of it. This tells you that it hasn't run for long enough, but this is just a demonstration. We won't go any further than that now. And then what you get in this column, your parameter values, and this is your 95%, 65%, 25% prediction intervals. Now you can actually do that on the reference. That's 65%, so that'll be the 95% prediction interval, for example. So one final thing on this, I mentioned that there's different types types of models you can use. So this is, I mean, thickness, SLD, roughness is fine for some things, but that's not usually how we want to look at things in soft matter. So if we just load a different one that uses one of the custom models I was talking about, I think it's this one. Let's go with this. So here, I think we've got 7 contrasts of lipid, right, at various iterations, but only 4 parameters: area per molecule, head thickness, and the parameter called theta. And the way that works, if we go to our edit project model builder again, you can see we haven't got the layer tab is grayed out, okay? And instead, we have this as custom layers, and we have our model 2B, which we've called it here. And this is written as a MATLAB script. And what this does is it takes your parameters in the order you've defined them and does various bits of things. So here's the basically the neutron scattering lengths and the compositions, and it gives you volumes. So obviously it can calculate the thickness from the volume divided by the area per molecule, and also from the volume it calculates the SLD. And then in the end, your output is you build these into layers. So this script just takes your input parameters and gives it out as layers, basically. And let's just cancel this. Let's go for a differential evolution again. And there we go. So it's quite a bit slower with a custom model, because it has to calculate your script every step. Okay, so that was the RasCal 1 bit. And so very, very quickly now, before we do the same thing in RasCal 2, I should point out the RasCal 2, what we've got here is just the calculation engine. And the key thing is it always takes 2 inputs. You've got a problem definition class, with which you use to define your problem, and a controls class, which tells you what kind of analysis you want to do. That's kind of all we need to know here. So if we can go and try and find the, yeah, so this one you can see, so this hangs a little bit, so you can see my computer problems on this one. But now we're going to do, if I can get it onto the right screen, we're going to do the same thing with our new toolbox. Oh. So now we want to do exactly the same analysis with the RAT toolbox. And as I mentioned earlier, this is a command line only, or a script only toolbox at the moment, so there's no user interface. So we'll see how we set up the inputs to this in a second. But the thing to note here, there's always 2 inputs into RAT, and we're running it from MATLAB because this is the only API we've got at the moment. There's always 2 inputs into RAT. The problem definition, which sets up the model that you want to fit, or the problem that you want to analyze, in exactly the same way as we saw with the RasCal GUI, and then a controls definition class that tells it what we want to do with this. So we can have a quick look at this now if we just make an instance of our project class, which is the main project input. And this is the class it creates, or it's a display of the class it creates. And you can see, just by looking through this, that it's very similar to the way things are organized on the main RasCal GUI, right? Yes, the main RasCal GUI. So you have parameters, you have layers, bulk, SLDs, scale factors, and so on. And so you can see that to build up the model, what you want to do is populate this class with the various parameters and so on, like we did exactly like we did with the GUI. And we do this by using the class methods, because if we have a look at the class methods, then you can see just from the names of these class methods, you know, add data, remove parameter, etc. By using these methods, you're basically able to build up this to analyze the model that you want. And we'll have a look at this. There's a script for doing this for our problem in a second. And the second one is the controls def class. Come on, MATLAB. So I don't know why that took so long. Now you can see why I'm recording this, because my MATLAB is really flaky. So here we go. Control stuff with properties, right? And at this at the moment, it's just set to do as just calculate. But if you do controls dot procedure is equal to, let's say, simplex, you can see that you have various things that you need to do, various things that you can set to control your simplex. And we should be able to, if we just do this, actually, if we throw in an error, there, you can see what's available is calculate, which will just do a single calculation, simplex, which will basically do a simplex. You've got a differential evolution, you've got a Bayesian algorithm, and you also got a nested sampler in here for, excuse me, for doing Bayesian model selection or experimental design. So if we now go and have a look at our polymer layer example for Ozo, let's actually clear all the output from this. So we set up our project class, we make a list of our parameters, add those to the class. Now we group them into layers, same as before. Thickness, SLT, you don't, and roughness, hydration. You don't have to have hydration in these, you can just leave these out if you want. Then we do some setting with the bulk in, bulk out, set scale factor, read in our data, and eventually we group all this together into a contrast. Okay, now easiest thing to do is if we just run this and hope MATLAB doesn't crash. So now we've got to here. So if we look at our problem now, we have our parameters. These are grouped into layers in exactly as the same way as they were in RasCal. Got our bulk in, bulk out, scale factors. We've got a background setup and a resolution, which at the moment is still just a constant resolution, but that's about to be fixed. We've got no custom files. And then we've set up a contrast, which basically these names in the contrast. So it's the data, it's got polymer data, which is what we loaded in. Oops, where did that go?
I have a couple of minutes left, Arwel.
Sorry? So you can see this is a description of the problem in exactly the same way as we set up with the GUI. We should do one step here. Let's display this again. Let me scroll down. Come on, MATLAB. So now we've added our two layers, the oxide layer and the polymer layer, to our project. Now we make a controls class, as we just did, and we just send this to RAT. So because this is just restarted, this will actually take a little bit of time. This is where I mean where my MATLAB is pretty flaky at the moment. So it doesn't normally take 10 seconds. That was just initializing. Let's do this again. Problem results equals RAT problem result. Oh, there we go. Yeah, so 0.001 seconds. So yeah, I don't know what the hang up was there. That's my flaky MATLAB at the moment. So now we'll just plot this out just to see what we've got, which is usually, again, much faster than this. And there we go. So you can see, again, our initial guesses aren't really all that good. So now to do something with this, we can just change our controls class as we did. So now controls is set to do differential evolution. We will set the number of generations and now send this to RAT. And now it will do our differential evolution for us. This usually takes a little bit of time. Where we got to this. Sorry, this is much faster outside this MATLAB Live worksheet actually. So yeah, it's this MATLAB live worksheet that is slowing everything down.
Can we call it to a halt? Arwel?
Just to show
It's
that
about
it
25 minutes now.
is it? Okay then. Yeah, we can do this. Sorry about it.
No worries. I mean, the advantage of